in the design example that I'm about to share with you today, I'd like to talk about a Class AB output stage that is capable of driving rail to rail in both directions. And this output stage is called a Monticelli bias structure. It's a very well-known structure, and it's something that you just simply have to know and add it to your toolbox. It's something that I find myself using all the time. It's great for, like I mentioned, rail-to-rail operation. It's great for low-power applications as well, and I'll show you why that is the case. So to get right into it, the core of the structure is a current mirror on the top, which then branches off to two FETs. Like this. And then there's a current mirror on the bottom. And then, before we get into that, I'd like to show you how this actually gets biased. So, if we look at this node right here, if we put a PFET diode right here and bias it with a current, we'll call this I1, call this one I2, and this one I2 as well. If I were to draw a second PFET diode over here and connect that to the supply, like this. Well, let's go through the KVL loop now, okay? We drop down a VGS, drop down a second VGS, and then we go back up a VGS. And that will impress upon this node right here that I've put a dot on, VGS. It's virtually the same as this node right here. So if we were to draw a current mirror off of this node like this, and this was 1-to-1, this W over L of 1, and this was W over L of 1, then we know that this current would be defined as I1 because it's just a simple current mirror. Well, that can also be extended to that virtual node as well, that we are holding it at that virtual VGS such that we can provide a defined bias for something that we connect to that node. And that's exactly what we're going to do. I'm actually going to just copy this real quick and move it down here. Delete a couple things. Right. Okay. There we go. This should be good. Change colors so this is a little bit easier to see as well. So now, if we were to take this as a virtual connection and connect it to the supply like this, then because this is still a virtual VGS, then this output current right here, this what we call IQ, is going to be a function of the ratio of this this FET I'm going to call M1 and this FET M2. So if they were 1-to-1, then IQ would be simply I1. If this was higher, like a W over L, let's call it 10 W over L of M2, then IQ would be equal to 10 times I1. And we can do the same thing on the NFET side. So here we would also have a NFET structure such as this, and this would be, let me just move that. this would connect to a similar structure now. You have an NFET diode and a second NFET here, and then a current like that. And the same is true here. So if we were to look at the loop again, we're going to go up a VGS, up a second VGS, and then back down a VGS. So this is a VGS and this one up here is a VGSP, and we're virtually connected to that node right there. And depending on what that ratio is, then we can define those currents as well. We'll call this one I1 as well, and it'll be a unit device, and then this one will also be 10 W over L of M3. And that sets the bias current here. So we have the quiescent current would be 10 times whatever that is, which is nice because it works out to be a ratio, and that's pretty well controlled, and it's dependent on what that current is and not much else. And that's a huge benefit to this Class AB output stage, because typically a rail-to-rail output stage that looks similar to this does not have a defined bias point. If you look at like a Class B output stage, those can swing rail to rail, but the bias point is certainly not defined. It's a function of what your input and your output voltages are, and it's highly undesirable because it can vary substantially across PVT and across your operating condition. So that's something that we want to avoid. Now, this output current, because effectively what we have here is a virtual node here. When we are moving this VGSN or this VGSP with some differential voltage that's applied at the input of an amplifier, we get a characteristic that looks very much like what we expect for a MOSFET, where it's this quadratic function of voltage versus current. And and that's, again, highly useful for an output stage, because the other problem that we have with something like a Class A stage is that your maximum deliverable current at the output is a function of how you size the quiescent current, where that is not the case here. You could see that this kind of just goes up. Eventually it'll hit some limit. What that limit will be is the point where this VGSN just won't go up any higher. So we can do that in both directions, and what we get is a curve that looks not like what I drew, but like this. So this would be your IP versus the VID, the input differential, and down here you would have, okay, that was pretty bad. Okay, it's just, all right, you know what? Move that. So this should be pretty well centered about that crossing, and this would be your IN. So that's what it looks like. It's able to sync and source in both directions, and you get a significant expansion on the current from what this I min level is down here, and your quiescent bias point effectively. So if you were to set I1 to make up a number here, let's call this 10 microamps. Your IQ could be so this would be 10 microamps. Your IQ would end up being 100 microamps, and it's not uncommon for this expansion of current to go as high as a factor of 10 to 30. I like to be on the more conservative side, and I'll stay around 10 or so, but you can go higher depending on your application, and that's a huge expansion for relatively low power, and I really do like the benefit that it has, that it can sync in source, because oftentimes when you're driving a load, it can respond a lot better to something that can sync in source. So this here is the Monticelli bias structure. I highly encourage that you take a look at it, you try to understand it, and see if you can use it in one of your designs. It's something that is very useful. Now, something else that I neglected to mention is that because we have two signal paths here, and we've got this floating diode structure, when you add compensation, it looks a little bit different than what you would expect for a traditional Class A amplifier. You end up having a capacitor on both sides, plus an annulling resistor, of course. So that's what that looks like. Now, I want to show you one more thing. I want to actually insert this within a amplifier, so you have an idea of what that would look like. I'm not going to draw this bias structure or this other bias structure, because it's just going to clutter things up a little bit. But if we go back to an architecture that I really like, which is the current mirror OTA, I'm going to draw that real quick. So if we have a PFET input, such as this, okay. No surprises yet. All right. Okay. Now, up top we'll have the PFET mirror. Okay. And over here we'll have, this is where we will actually insert this Monticelli floating diode structure. Okay. And this is how we would make a rail-to-rail output stage. All right. So that would be your V out. And one more thing that I would like to point out is that if we have a tail current here that we'll call this I, it will split up here as I over 2. Same on the other side. And if we assume a 1-to-1 mirror here and a 1-to-1 mirror here, then this current is I over 2 as well. Now, when we size these diodes, the floating diodes here and here, what you need to keep in mind is that the current flowing through either one of them is not I over 2, it's I over 4, because we want that to be symmetric. We want that to split evenly. So it needs to be I over 4. So when you go back to this diode structure up here, where we have I1, if I1 is equal to I2, if I'm drawing up top, if I1 is equal to I2, then we would want to have a 2-to-1 ratio here, right? So this PFET here would be 2, and this one would be 1. That way we could split the current. And that is true here as well. So that's something that you need to keep in mind. You want that to be split evenly. If you don't have the right bias applied to this, it'll be pretty easy to tell. If you are running a nominal simulation, you should see pretty close to a 50-50 split between the two. If you've got a poor bias applied to it, what'll happen is you'll see that one side will practically steal all the current, the other side won't be on. And that's something that, while it might be okay for your amplifier, it's not ideal, because it can result in weird transient settling and recovery issues. So just try to avoid that if you can. Okay. The last thing that I would like to show regarding the Monticelli bias is how exactly it can achieve rail-to-rail operation. And in order to do that, I need to show you a comparison of the Monticelli bias and a more traditional architecture. So on the left, I'm going to put the Monticelli. And then on the right, I will put traditional. Right. To draw that, we've got the P-FET up top, the N-FET on the bottom. We'll call this 0 volts and we'll call this VDD. And then for the more traditional architecture, what I'm going to draw is basically the device is flipped where we have the N-FET on top, P-FET on the bottom, same splice. So just to draw this a little bit more, typically what that will look like is N-FET, like that, and then a P-FET down here, another current. And let's go back to the Monticelli really quick. If we look at the output here, if you're very careful with how you size the overdrive on these FETs, such that the requirement for staying in saturation is small, you want a very small overdrive on that output, then you should be able to achieve near rail-to-rail operation. If VOV is small, then effectively while you're losing gain as you start approaching VOV, you still have enough that you can actually drive to the rails when you're near either supply rail. Now, if we look at also the other thing to keep in mind is that what's driving these gates is actually going up, right here for the N-FET, and it's going down for the P-FET. So that's expanding away from the rail, and there's no problems with that from a headroom perspective. Right now, if you look at the example on the right, the opposite is true, that as we start sinking and sourcing more current, in order to provide the necessary gate drive, we actually have to expand towards the rails here. And that can be quite problematic, because if we're at an output here of VDD, then what that means is we have to go up a VGS here, and then we have the headroom limitation on this current mirror, which for a simple current mirror might just be an overdrive. But that means that we could never truly get right up to the rail for this output stage. And that's the price that you pay with that traditional architecture. It's a well-defined bias, but you can't go rail to rail. And that's why the Monticelli architecture can be a more attractive alternative